In this video we're going to look at finding the conjugate points to an ellipse which has been generated by an object travelling under an inverse square law of attraction. So this equation here, which we have derived in the previous video, is the polar form of a conic, and we can see that the values b and c are constants and the value a is a parameter which is dependent on the speed. So this equation here is the polar equation of a conic, where E is eccentricity, such that we can say that in this equation C equals A1 minus the value of C squared, E squared, sorry. Now we can take this A1 minus E squared upon R and we can put it back in the original equation, and that's what we've done here. Okay, so we've ended up with this equation here. Now this equation number 1, you'll find that equation in the book, and it's got a particular geometric description. If we take 2 points which are focal points, and then we have the angle beta is the angle that the line between the focal points makes with the x-axis, then the angle theta is the angle that a point will make with that x-axis, and that a1 minus e squared is given by that little blue section there. Okay, so we can then say that c1 equals e1 and the c2 equals beta. We say that theta is the independent variable and r is the dependent variable, and then we can use this equation here, which we derived in a previous video, to find the values of the conjugate points where the value of theta equals 0. Okay, now I've spared this up because I don't want to get through the full derivation and read it out, so we're going to use the differentiate partial r by partial beta, and also the partial r by the partial epsilon. Now that's what's happening here. Now you can always slow it down, have a little look if you're really interested in it, but also I'll put down a note down below where you can download a PDF copy of this derivation in my own handwriting. So we were left with this equation which gave us the conjugate points, but we're going to have to rewrite it and we solve it for theta, and the solution with theta looks like this. Now I'm not going to get through the full derivation of it. I've derived it and I've put it down below, and you can download it if you want to. Okay, so the upshot is if theta is equal to 2 tan, and we'll call that inside the brackets alpha, then if alpha is greater than 0 and less than 2 pi, then it means that the angle AOB, which is the vectorial angle of the conjugate point, is less than alpha. Then it means we have a minimum. If the vectorial point is greater than alpha, we have a maximum.